Good afternoon, sir. This is Manav Jaiswal, 19BCE1037, and I'll be presenting today the assignment 3 video presentation on the topic past and present trends of mining. So basically, what is Bitcoin mining? It is the process by which Bitcoin transactions are validated digitally on the Bitcoin network and added to the blockchain ledger. It is basically done by solving complex cryptographic hash puzzles to verify blocks of transactions that are updated on the decentralized blockchain ledger. So, uh, who does the Bitcoin mining? Basically, Bitcoin mining is done by Bitcoin miners. So, the basic 6 tasks that Bitcoin miners have to perform are the they need to listen for transactions and validate them by checking that signatures are correct and outputs being spent haven't been spent before. That is, there is no dollar spending involved there. Then they have to maintain the blockchain. Start by asking nodes for historical blocks before they join, and they have to listen for new ones by validating the transaction and the valid nodes. They also need to assemble a candidate block. Once miner has an up-to-date copy of the blockchain from their peers, they need to begin building on their own blocks. They need to make sure that each transaction included in the block is valid. They need to find a nonce that makes the block valid. This is basically what the key of Bitcoin mining, and it will be discussed later by me. And this step requires the most work, and it poses all the real difficulties for miners. And they need to hope that others accept their block on the consensus chain instead of others. And if it is accepted, they get the profit. And transaction fees, if applies, given to miners on a 1% scale. This is the basic structure of finding a valid block. So basically what happens here is the first thing that a miner has to do is to compile valid transactions pool into a Merkle tree up to the limit of the total size of the block. Header headers in each node basically points to the previous block, and the header nonce field is tried to find a nonce that causes the block hash to be under the target. Basically, there is the required number of zeros, and that validates to the 32-bit value the hash can have. If none is valid, we need to change the nonce, and if not by header, then we use the transaction nonce, and then back to the header nonce in succinct order. If if it is successfully done, then the whole Merkle tree changes upwards, producing a more expensive operation than looking in the header operation. And when a combination finally hits, the miner has to announce, and they hope for the profit if their block is validated, accepted. If the block is accepted in the chain, then we talk about the difficulty of the finding a block. Basically, this difficulty changes roughly every 2 weeks, and the like we can say that it changes at around every 2016 blocks, and difficulty fluctuates based on given time to mine. The time that is given to mine that block basically governs how much the difficulty is in mining the block. Miners on the same block have the same difficulty, and it allows consensus. Then this is the graph for the Bitcoin hash rate versus difficulty. So what happens here is that mining difficulty is basically dependent on amount of miners and the effectiveness of hardware, and the exchange rate of the coins is always increased. So it takes roughly 10 minutes to find a block. Hexadecimal value that needs to be below, and the calculation is about 267 ounces. And this is the graph which represents the hash rate versus difficulty. So then coming to the mining hardware, so the core of the difficult computation miners are working on is the SHA-256 hash function. So basically it is applied twice to a Bitcoin block, and then we'll be now discussing about the what are the trends we have in the mining from the past to the present, like CPU, then GPUs, then ALUs, FPGAs, and integrated circuits as well. So coming to SHA-256, So basically SHA-256 maintains 256 bits of state. The state is basically split into 8 32-bit words, which makes it highly optimized for 32-bit hardware. In each round, a number of words in the state are taken, some with small bitwise tweaks applied and added together mod 32. So this basically this is the structure of the SHA-256 as shown on the screen, and the entire state is then right shifted, with the result of the addition becoming the new leftmost word of the state. So this is basically what happens in the SHA-256 algorithm. This is a gist of what happens there. Then the task for miners is to basically compute this function as quickly as possible. Remember that miners are racing against one another, so the faster they can do this, the more they will earn. So they need to be able to manipulate 32-bit words, perform 32-bit modular addition, and also do some bitwise logic. Then coming to the professional mining that we have here. So basically mining went from CPUs, GPUs to FPGAs and ASICs, and it is like in similar to what happened in the gold mining, from gold pan to the pit mining. So in the beginning of mining, there was the era of CPU mining. This was the first generation of mining. CPU mining was as simple as running the code, and they basically searched over nonces in a linear fashion, computed SHA-256 in software, and checked whether the result that they found is valid or not. And if this process would have been followed, it would take several 100,000 years on average to find a valid block. So this is not a feasible option. So then GPU mining came into the picture, and GPU mining basically has many advantages over CPU mining. So they basically provide high throughput and parallelism, and they are very easily available, and amateurs can also be able to perform GPU mining, and they're very easy to set up. And there is one important feature that GPU provides is overclocking. Overclocking basically GPUs basically can be overclocked, meaning we can run them faster than what they are actually designed for. But it has some demerits, that it leads to errors, but the net rate of validating an invalid solution is still less than the outputs being produced using normal CPUs. And there are other disadvantages that we have with GPU mining, is that they can't work side by side. Like we can't club more GPUs together for a single task. And one of the major issues with GPUs is that they overheat, and the amount of electricity needed for cooling as well as working of GPUs is very high. And even if we club hundreds of GPUs together, we to find a block, it would take like hundreds of years to find a valid block. Then FPGAs, field programmable gate arrays, came into picture. Basically, what happens is the rationale behind FPGA is to try to approximate the performance of custom hardware while also allowing the customer, the owner of the card, to customize it. And basically, they provide better performance than GPUs, definitely. But what the issue is that the overclocking here leads to errors, and in comparison to GPUs, we can say that cooling is easier here, and also the stacking is very easily possible here. FPGAs allow stacking very easily, and but the issue here is that the common miners can't use this because it is not very easily available in the market. And FPGA mining lived it lived a very short-lived phenomenon. Uh, Overclocking and being on all the time led to many errors and malfunctions in FPGAs as well. And it turned out to be difficult to optimize 32-bit addition step, which is critical in doing SHA-256 algorithm, as we discussed before. And as I told, they are very less accessible, and so amateurs, people, or new starting miners cannot implement this FPGA mining procedure. Then the main thing that we have today in hardware mining is basically the integrated circuits. We call it application specific integrated circuits. They are basically designed, built, and optimized for the sole purpose of mining Bitcoins. ASICs require considerable expertise, and their lead time is also quite long. The first few generations of Bitcoin ASICs were quite buggy, and this led to some confusion between the consumers and the manufacturers. Consumers often experienced shipping delays with boards nearly obsolete by the time they arrived. So basically, this led to the lifetime of ASICs quite short, because then the mining centers came into picture, and in the beginning, it basically ended all around about 6 months for integrated circuits. Then for the current scenario, basically what we have is that there are very less individuals working as miners, and there are mining centers who work as a professional miners today. And for a mining center, the main things that they consider is that where they need to set up is that they consider the climate, the cost of electricity, and as well as the network speed there. So currently, ASIC mining is the only realistic means to be profitable in Bitcoin, and it's not very friendly to small miners. And some examples of mining centers that we have today is the Bitfury Mining Center, which is located in the Republic of Georgia. Then coming to the energy consumption, the Launder's principle basically what says is every time you flip a bit, there is a minimum amount of energy required. And the three steps to Bitcoin's usage of energy is basically the embodied energy, pure electricity, as well as the cooling. And there are two ways to calculate the energy consumption we have in the mining. So the top-down approach, which says which is calculated based on amount of bitcoins mined and the value of them. And there is the bottom-up approach, which basically is based on number of hashes and the estimated power consumption of these hashes. Then coming to the mining pools, basically there are very small chances of finding blocks in the mining pools. So small miners basically join together to form mining pools, and they work on finding a single valid block. So calculating mining shares by reporting near valid hashes and actual valid blocks is done by basically four methods: pay per share, proportional, pool hopping, and communication APIs. Basically, what happens in pay per share is even if blocks are not found, high fees is paid and they're prone to attacks. And in proportional, every time a valid block is found, fee is paid based on the work done by each of the individual involved there. And pool hopping is basically jumping ships between two models when they are most valuable. Then talking about the risks that are involved in mining, there is forking attack, cold finger attack, forking via bribery, temporary block withholding attacks, blacklisting. So let me go through each one of these. So basically, forking attack refers to the basically essentially paying a transaction and then mining on a different block to invalidate a recent transaction. If an attacker has majority of hash power, it can be countermeasured. Then Goldfinger, basically, when the motivation is not to profit directly through Bitcoin, but instead to bring down the currency or the network, this is called the Goldfinger attack. Then bribery basically happens in mining pools, where mining pools are at loss or because of the biggest tipper. And withholding blocks is basically referred to finding more blocks on top and then declaring longest chain. This is more theoretical kind of risk that we have. And punitive, the goal here is to blacklist or censor Bitcoin addresses owned by certain people so that they can't spend any of their Bitcoins any further. So these are the mining risks involved in basic risks involved in mining, and this is all about my presentation. Thank you, sir.